Okay, so first of all, thanks for Jean-Daniel for inviting me. It's a great pleasure to be here and also hope to work with at least some of you. Secondly, I apologize for speaking English. After 3 years in Alliance in high school, I gave up on the French and moved to computer science. I hope that make it better in computer science. In this talk, I will talk about my expertise related to what is known as core sets and explain what it is. A short connection to both robotics and big data, and combine it to theoretical, the computational geometry, which is my original background. I'm a former student of Chaire, as Jean probably said. And we'll start with what we're trying to do today. So we want to talk about computational geometry and introduction to core sets, the relation to machine learning of big data, and cool robotics. And in practice, it means in the computational geometry, we talk about Carr-Theodori theorem and the approximated version that we suggest. We then talk about core set from inquiries that related to this problem. We talk about Google PageRank in the context of big data, and real-time pose estimation. And it's all supposed to be connected, although it seems quite different. Maybe use this one. Yeah. Okay. So some introduction. What is big data? Just a buzzword, but formally, usually we talk about high-dimensional data, large amount of data, and the data come on the fly. So unlike in Corman, introduction to algorithms, we don't have just data that stay in memory, just keep coming, like in the web application, in mobile phones, and so on. So theoretically, we talk about streaming algorithms. So the memory is only logarithmic. So you have endpoints that you saw till now, but the memory is only logarithmic in n. So we need to solve the algorithm in this model. Second thing is we want parallel algorithms because we have cloud now. So, and we don't want to use the traditional parallel algorithms because it's too complicated these days. Yes?
I don't know if anyone knows, because I don't know the word. What is it a hardware concept, the logarithmic memory or something?
No, it just means that if n is the size of the data, so you have millions of, this is the number of points you have, okay?
The number of bits?
The number of bits, for example, okay? But the memory, so you have petabytes of bits, okay? Petabytes of, so you have petabytes or terabytes of data, but the memory on my laptop is just log n, because I have a few megabytes only, not petabytes. So I send you billions of bits to my laptop, but the memory is only log n. It's only a few megabytes. So I need to read terabytes bytes from the hard drive.
You mean the complexity of the memory of
yeah.
a word of n bits is not 2 power n?
Yeah, so let's talk practically. So suppose I have a hard disk with a few terabytes, okay? But the memory here is only a few megabytes, 100 megabytes in my laptop. And I want to solve the problem on the data from the hard drive. So I can scan all the hard drive, right? I can scan it, but I cannot put all the hard drive in the memory on the RAM of my machine. So I can read all the data, but cannot remember only the data because I have only a few megabytes of memory. So I scan the data, but I am allowed to use only log n a few megabytes of memory. So the size of the data is huge, but my memory, my RAM memory, is extremely small. Theoretically, you have all log n memory, but the input is n. So n is the number of the points it's stored till now.
You mean it's a mean of contracting the real space of memory in a few.
Exactly. So you cannot assume if you work in Facebook, you cannot assume that all the Facebook is on your machine. Your machine can only store just a small fraction. You can read everything, but you can store a small fraction.
How can you not lost information in contracting?
Are we lost? That's the problem. Okay. But I try to do quite good. If I want to sum, I won't lose anything, right? If I just want to sum the numbers, I can still scan, I won't lose anything. And then we need to remember only the sum of the numbers that I saw till now, right?
My English is very...
Okay, I'll continue. I hope that other people understand. So we want a parallel algorithm, but not in traditional parallel algorithms. We want that everything will be very simple. So officially, they call it embarrassingly parallel algorithm. And if you know a map reduce or merge reduce, it essentially means that you just run the process independently on each computer and then collect the data. And you don't need actually to handle all the parallel complexity and communication between them. So, and unlike maybe if you heard about online algorithms and stuff like this, we don't assume anything about the order for the data. This is uniform or nice. Maybe all the important points will be in the end, important data. So no assumption on the order of the input. And if n is the number of vectors seen so far, log n is the memory that you have. Now we have m machines on the cloud. So every time that we get new point, we want the update time will be only log n over m, and all using the m machines. And intuitively, the idea of core set is instead of just suggesting better algorithms to solve a problem, right? In computer science and computational geometry also, someone suggests algorithm 2 to the n, that someone come and say, I have algorithm n to the 5, and someone said, I have n to the 4, and we keep improving the algorithms over time. This approach said, let's not improve the algorithms. If you have data D and the algorithm A, and you want to compute the A of D, we want to run algorithm on the data, and we can't because the data is too large, it will take forever, or we get out of memory. Instead of suggesting better algorithm A, let's reduce the data D to C. C is what I will call core set. And the challenge is to prove that if you run the algorithm on the small data C, we will get approximately the same result as if you run it on the original data D. Okay, so there are two questions here. I mean, first of all, what does it mean to approximate? We need to define it formally. Secondly, what is this C? Is a subset, a weighted subset, just number of bits? Definitely should be small. And of course, it's not clear if user exists such as C. Maybe we need to take all the data to solve our problem. What can we do? So I will define it in a few slides. In general, we define it differently for every paper. So the core set definition is really more a buzzword, and every paper we define it according to the problem. But the idea is we want provable guarantees on the approximation, both for the size C and the error. So intuitively, we want the core set size will be something like 1 over epsilon, and the error will be epsilon. So you expect a trade-off between the compression and the error that you get, but we hope it will be much smaller than the size n of the input. So probably the most famous core set is just uniform sampling. Because you said to engineer, I have petabytes of data. I want to know how my customers look like. So we said, let's just take a sample, random sample from the hard drive, run the model, do clustering, whatever. And we hope that if it's good, if we do find 2 clusters in the model, in the sample, it will probably work for the original data. If you want to know who will be the next president, we do random sampling. And we hope that if we do random sampling, 99% of the people say something, it's probably be the truth. Of course, we have small error. So if exactly half say this and half say this, we're probably in trouble in predicting. So what's so wrong with uniform sampling? So sometimes it's work weight, like in epsilon nets, for example, or epsilon approximation, if you learn it, and actually we'll use it a lot. But in general, suppose that you want to cluster the data, and you just do random sampling, which are the blue points. So in general, Hoeffding inequality said that it will be good, but the problem is it depends on the maximum diameter of the points. So for example, we won't have any representative here. So suppose that you have millions of points, and 5 people extremely far from the others. So we probably miss this. Now, maybe it's outlier, but maybe actually these are the rich people, or these are the terrorists. Sometimes these are the very important points, and random sampling is a bad idea. We want to catch them. So the error that we'll pay if they are very far from each other might be very good. For example, if you want to run 2-min clustering, this is important clustering, we just miss it. We put the 2 centers here, while we need to put another center there. Please feel free to ask questions online if you want. So just an intuition problem. One of the courses with Nir Suchen and Michael Fagin for image processing was noise removal in high definition image. So we have a video, we want to remove the noise. The problem is that the existing algorithm works only for a low definition image, but we want to run it on high definition images. So the algorithm essentially takes the noisy image and return you the clean image by understanding the structure and the patterns in the image. So what we suggested, so when we called that, we talked with the authors of this paper, Michael Elad for the technical, they said, okay, just use uniform random sampling because we got out of memory when you run it on the high definition image. But the problem with random sampling, if you look, for example, in this image, if you do random sampling, you just get green points, and you miss all the patterns of the woman. If you do random sampling here, you just get 1 point. So if you want to understand the patterns in the image for good compression, it's not such a good idea to do just uniform random sampling. So maybe the most powerful idea behind Coreset is not only the idea that we can compress the data, but actually the idea that we actually run it independently in parallel and for streaming data. So suppose that we have an offline algorithm to just take, I don't know, 20 points and we reduce them to 10 points. And it's offline. It's coded in MATLAB or Python, only on my machine. And it's also very slow. Say n to the 3 for n points, but it promises you to reduce the endpoints to 1 over epsilon for some small epsilon, which is the error that we want. So, but it promises that for every n points, if you give me, for example, k segments like here, the sum of square distance over the original data and the coset, which are the red points, is approximately the same, up to 1 plus epsilon error. But now you want to run it on terabytes of data on streaming on the cloud. So there is a magical framework, actually well known in computer science from the 70s, that we just apply on Coresets, that said that if you have just code for offline data, you can run it on a huge amount of data using the following trick. If you know, it's called sometimes merge and reduce tree. And the idea is this. You just take the small set of points from the stream and compress it. So your compression algorithm is slow and need everything in memory, but since this is just a small set, you can just compress the first 2 epsilon points to 1 over epsilon. And because the running time is n to the 5, n is small, it's only 2 over epsilon to the 5, we're good. Now we take the next chunks in the stream and also compress it. Now the problem with this approach is eventually we'll have too many compression on memory, and the memory will explode, because these are tiny subsets and we have billions of points. So what we do now is we take the union of these 2 compression, delete the original constant from memory, and then compress them again. So we do merge and reduce every time. So now we have compression of these 2. So this is actually a compression of a compression. Then we can take the next set of points, take the union, compress again. Take the next set of points, take the union, compress again, and so on. And in every given moment, we'll have a small amount of points in memory. So my few megabytes in computer will do. And the running time will be fast because we always run the compression algorithm on small data. So we don't care that it's very slow because the input is very small. So what is the bug in this approach for me? So what is the problem for what I said now? Just take the next set, union, and compress. Take the next set, union, and compress. Do you see some problem here? What will eventually happen? OK, I'll give you a clue. So this was approximation, say, 1 plus epsilon. And this was 1 plus epsilon approximation. This is approximation of approximation. So it's actually 1 over plus epsilon coset for 1 plus epsilon coset, which means it's 1 plus epsilon squared coset. Now, after millions of such sets, the error here will explode. It will be 1 plus epsilon to the n after n points, or epsilon n points, which is about 1 plus epsilon n, which means that we will have a huge amount of error. So instead, what we do is we don't union this one with this one. We continue, merge these 2, compress, and then we still have 1 plus epsilon squared error. Then we take the union of these two cosets, compress them again, and we have some in the binary tree. Now, how many levels we have in a binary tree if you have n leaves? Who knows? Logarithmic, right? So the error will still increase over levels. Very good. The error will still increase in every level, but only logarithmically, which means that in the end, the error will be 1 plus epsilon to the log n, which is about 1 plus epsilon log n using calculus. And this is small, so we just run the algorithm with epsilon over log n instead of epsilon. And then we get 1 plus epsilon error. So it means that, and we implemented these systems in Spark, if you know Spark, which means that when a new student develops new courset, just put a pointer to this courset algorithm, and then you can run it for streaming data. But this is for streaming. What about the cloud? So how can we run this in parallel on the cloud, this compression scheme? Any idea? So all the corsets here are quite independent of each other. You can compress this independently of this. So why don't you just send each corset to a different machine and compute this independently? So the problem with this approach is that we need to get all the data, send it to the machines, then the second level and third level. But my first student in Haifa, Altenberger, complained that it take a week to upload all the data to Amazon Cloud and another week to then compress it. And he wants that while he uploads the data to the cloud, to compress the data already. So you want both streaming and distributed. So to this end, so there's just this approach, which means if you have, for example, 2 machines, and you have infinite stream of points, just take the odd corsets to be computed by the first one, and all the even corsets, or the even subset, to the second one. So like ours, you just give them each subset to a different computer. Each computer gets a stream. This one gets a stream of the green points. This one gets a stream of the pink points. Every given moment, you can ask each machine to give you the corset of its points to the main server on top. This will also take very low communication, because you only need to send the corset. And that's how we can divide the time by 2 if you have 2 machines, or by 10 if you have 10 machines, just by splitting the points around it, so we can have both streaming and distributed computation, like I promised in the beginning. Actually, in robotics, this is from an autonomous car in England, and people suggested, why delete this tree from memory? We have large hard drive. Let's keep all the corset. So if you have image from autonomous car, we can take all these trees and zoom in for specific time segments. So what we see here is image collected over time. And every time we take the corset, the original data, and compress again. So every node is the representative of the child node of the node. And now you can zoom in and zoom out. We do some nice user interface that you can zoom in and zoom out for a specific time interval. So you're just throwing the tree. When we talk about streaming data, this is in MIT. So one of my students ran with a smartphone and collect GPS points with video. Here you see the GPS points, but the number of points that are sent to our lab is only this set of points. And what we had to prove is that we select a very small sample of points on the smartphone to save communication and save to the lab only a few number of points, but still we can estimate the path based on these points. So for example, if we're just running going on a line, we don't need to send too many points, just 1 point in the beginning and end. But in general, it's hard to estimate when is the right time to send points. So we just define courses for this problem formally, solve the problem, and then implement it as in the streaming tree that I just saw you on the smartphone. In real time, you collect point, and you set the streaming point to the lab. When the lab have too many points, they send it to Amazon Cloud and so on. Next, we do this the same with the Google Glass that were very popular at this time. And we try to segment video in the same sense. So this is the big data part. And over the year, we designed such courses for many different problems with very different people in different fields. And I hope that one of the main reasons that I come here is also to develop new core sets, and already suggested to design core sets maybe for topological problems, which we still don't have in the list, and it will be awesome to have some. So in the course of robotic, let's see. So talk about big data. In robotics, we don't have big data. Sorry. So in robotics, we don't have big data, but we have real-time data. So I had in MIT, you have huge drones that cost thousands of dollars, quadcopters, and you must put a helmet on your head because they're very dangerous. And when it broke, you need to send it to Europe and a lot of money to repair it. So I decided in Israel that we use only very cheap drone that I buy from Amazon of the mall, just $20. The problem that it's very unstable because it has no sensors at all, as you can see. So this is with remote control. And the idea was to get rid of the remote controller and have an algorithm that you control the robot instead of your hands. So we used two PlayStation web cameras, each one $10, less than $10 in Amazon, 2 Raspberry Pi, which is just mini computers, and the drone that we bought with some markers on it. And we put it all over the university. And the idea was that if you come, for example, to a hospital, you can say the name of the patient that you want to visit, and the drone will just take you there in this complex. So we started on the university. We now run it on the mall near the university, and we hope that soon we'll be able to show it on hospitals. So you say, take me to the lab of Dan Feldman or the secretary, and the drone just takes you. There's no hidden remote control here. The algorithm controls these drones, and a human cannot actually be so precise. If you try to play with them, you have a huge error even if you're an expert pilot. So in this version, you see we have cameras around, the very cheap cameras around. We control the quadcopters and try to tell him what to do, like a human with a remote controller. Now, the main challenge here was that the hardware were too weak. So we cannot use existing algorithm to track the quadcopter. So what we did is we have a $1 million system for tracking the drone, but it is extremely expensive. You want to do the same with our cheap web cameras. So we had to develop algorithm that will just track few points on the quadcopters, on the drone, and we'll try to stabilize it only using these few points that you track. And the question again was, what points to track? So what you see here is just uniform sampling. You see that it's very unstable. Actually, when we go a bit back, the drone just crashed in the wall. This is using our core set that I will define formally in a few slides. And this is the other version is with the expensive system. So this is with the low-cost system with our algorithm. Next, you can see with the existing algorithm, we just call RANSAC, uniform sampling. And next, we actually used more visual features. So let's see how it looked like. So you just put some markers on the drone, and this is what's called SIFT. In computer vision, it just means edge detection. And each moment, we try to understand how the points move to stabilize the drone. But we have too many points to track, and we need 30 frames per second. So instead, we choose only 5 points every second, and choose only them for the next second. And the main question is how to choose the right point to make sure that if you track the points, you will track the original data. Sorry. Good? Yes. Okay, so now we want to go back to the theory part and explain more precisely how exactly we're going to do these things. So end of the fun part, let's try to talk about the geometry behind these problems. So suppose that you have endpoints, even on the plane. And now I give you a query point in D-dimensional space. So this is some facility, but I'll give it only tomorrow. And I'll ask you to sum the square distances between the query point to all the other points. For example, suppose these are people, and I want to have a new train station, and I ask you what is the sum of square distances from the people to this train station. And I have several options. Maybe I want to compare them to minimize the sum of square distances. So the question is, first question, how much time it will take to compute the sum of square distances? Anyone knows? You have endpoints on the plane. I give you a query Q. How much time it will take you to compute the sum of square distances from the point to this star? O of. So you take linear time. We have endpoints. The distance is O of 1 is constant time. So the running time is just O of n. You just need to compute n numbers. But the question is, if I give you the points today and the query tomorrow, can you do this in milliseconds, in O of 1 time, by preprocessing the points from the beginning? So the answer is yes, you can precisely compute this. Without knowing Q, you can preprocess the points. So tomorrow, you can answer in O of 1 what is the sum of square distances for any Q that I will give you. Any idea how to do this? With confidence, any idea how to do this? How we can compress the data in smart sense? So then we'll have the Q will approximate the sum of square distances. So let's see. So the distance between the point and the query is just the norm P minus Q squared. But this is just norm P squared plus norm Q squared minus 2PQ, right? Think, for example, like high school, you have two numbers, A minus B squared is exactly this. And we want the sum of this. But the sum of this is simply the sum of this, the first term. We compute it at night. When you get Q, we just multiply it by n because the sum is over n times this one. And for the last term, we have sigma, but we can put the sigma inside. And then we can compute this in advance, and then just multiply it by Q. So this is easy. The problem that when we want to track a drone, we cannot track the mean of the points. We can track specific points of the drone. We cannot track the sum of the points. So what we really want is a small weighted subset of the points. Not just sum of points, just representative points, such as the mean of this representative will be the same as the mean of the original data. And one idea to do this is just use uniform random sampling for about 1 over epsilon points. So we'll give you epsilon error. But the problem with this approach is that it will fail with high probability. And the problem is that the drone needs to compute the mean 30 times per second, which means that after a few seconds, you probably got crash in the wall. So what you want is the deterministic algorithm to compute the mean, a good approximation to the mean that will answer these kind of queries. And it was a very surprising problem because it looks very easy, but still it was just accepted to one of the top conferences in machine learning. And it's quite amazing in the 21st century, we still only now know how to take a subset deterministically that will answer this simple basic question. And we show many applications. One of them is Google PageRank. So in Google PageRank, we have a metric G, which is the graph of people, of web links, for example. And you can scale the columns to have sum of 1. And this is called damping factor. And from G, we compute what is called positive stochastic matrix A. And we know that by Perron-Fabinier theorem that there must be a vector x positive and sum to 1, such that ax equal x. This is what is known as the PageRank vector, because it says the value of x says how much important you in some sense in the network. If you just define b to be a minus I, ax equal x means bx equals 0. And the challenge in PageMac is to compute this x efficiently. But if you talk about coarse set and approximation, we want a sparse version of x such that bx won't be 0 maybe, but it will be almost 0 in the sense that the norm will be less than epsilon. In particular, if your importance, if your value in x is more than epsilon, you have a representative in x prime. But it's exactly the same problem that we saw in the previous slide. Why? Because x's distribution over the columns of B, so this is just mean that the weighted mean of the columns of B is 0. So what we ask here is a small weighted mean, which means a subset of the columns that will approximate the mean 0 up to some epsilon. So this is essentially the same problem I just discussed before about approximating the weighted mean of a set of points. So, so how we do this? So again, in the case of quadcopters, I already explained the motivation. What is exactly the problem in the case of quadcopters? So we have the cheap camera, and this is the formal question. We have a few markers on the drone. This is a set of point P on the ground, and now we look at the drone here, and we want to know where is the drone now, how it moved. So for this, we can just translate the points, compute the vector of translation, and we say, okay, if this is the set of points and the drone just was translated, we can just, it means that Q is just P plus some translation vector. And if we just take 2 points, look at the difference, this is how the drone moved. This is easy. In practice, we have a lot of noise because of the resolution of the cameras. We have a few frames per second. We have latency, communication, the camera moves, and so on. So actually, we have usually we can assume Gaussian error, which means that it's not exactly fit. So you have some noise. And then a natural question is, what is the translation T that will minimize the sum of square distances from P to Q? So among all the possible translation, what will minimize the sum of square distances? And the solution is essentially the mean. But a much harder problem is what if the drone not only translate but also rotate, which what happens in practice. So now the question is, find me a rotation and translation of P so as to minimize the sum of square distances to the point of Q. So now we have another variable, not only translation, but we have a rotation matrix that we want to find that will minimize the difference between the observed set and the original set. If you know how to minimize this distance, we understand where is the quadcopter now, then we can track it and calibrate it. But it's not all. Actually, there is, I assume in the previous slide, that we know which point belongs to which point, the matching. This is actually the hardest problem because we have too many permutations that we can choose. And we need to know how to assign which point in the which red point belongs to the observed green point. So actually, we want to minimize not only the translation T and the rotation matrix R, but also over all the permutation of Q that will minimize this. So this is strongly related to matching problems that you probably heard about. But I first discussed about only the rotation problem, which is also a simple solution. So if you have only translation, it's just the mean. If you also have rotation, it is a simple idea that says if P is the original set and Q is the new set, so it's n by 3 matrix, each one of them, n rows and 3 columns of x, y, z. Just compute what is known as the Svd decomposition, the singular value decomposition of the matrix P transpose Q. You get 3 matrices, U, D, and V transpose. This is known as the PCA or SVD. And the optimal rotation is just V multiplied by U transpose. This is well known many years ago, but we want to compute it fast. So let's now define what is coarse set for pose estimation. So we want to track only few points the purple point, not all the weight points, because we have many of them, such that in every given moment we know where is the drone just by looking only on the purple points. So formally, we want a weight vector, so weighted subset of points, so the green points, such that for every rotation and translation, if you compute the sum of square distances of the rotation and translation on the original data P and Q, and if you do this only for the weighted point, you get the same result. And of course, we want that most of the weights will be 0. So we can ignore most of the points. And the question, can we do such things? So of course, we will not solve today the matching problem, but know that if you need to follow only few points, the number of permutations for few points is also smaller. So this is actually, if you don't know the match of this point, it doesn't matter because you only need to match these points, which is how the coset also helps to solve the matching problem efficiently. And let's see how it looks like. So we want to compute the SVD of the sum. This is P transpose Q. This is the matrix. We want UDVT for this. But this matrix is just this matrix, the sum of each point in P to a point in Q. This is 3 by 3 matrix. So we just want to sum 3 by 3 matrices. If we just concatenate the matrix to a vector, we get a vector, a sum of vectors, each of 1, 9, so which is the 9 entries in this matrix. And what we're going to do is to approximate the sum of these matrices, the sum of the vectors that you see here, but a small weighted sum of matrices. More precisely, we take the matrices as vectors, we have sum of vectors, and we choose a weighted sum of vectors that will be exactly the same, no epsilon, exactly the same as the original sum. The number of points will be only with the dimension, which is about 3, or in this case, 9. For machine learning, we actually want something better, so we use epsilon and have a result that is independent of D. So the last ingredient that we need is the Carl-Theodori theorem. So what the Carl-Theodori theorem says, it says if you have, how much time do I have? OK. So suppose that you have 4 points, and I choose a point in the middle. Maybe this is the weighted mean of the 4 points. So the weighted mean of the 4 points is somewhere inside this square. Whenever you choose this point, you can actually have a triangle that covers this point. See, if you put it here, you have these 3 points. If you put it here, you have the other 3 points. So whatever point you choose, you can have convex combination of only 3 points out of the 4 that will span the same point. This is true also if you have a polygon. So whenever you put a point here, you always find a triangle that covers this point, which means mathematically that you have a convex combination for only 3 points, that the sum of these points will give you the green point. This is true for every polygon in two-dimensional space. No matter how vertices you have here, you will always have a triangle of 3 points. This is the Carl-Theodori theorem, but it actually works in high-dimensional space. So in any dimension, if you put a point inside the convex hull, you can always find at most d+1 points. So it's independent of the number n of the original points, which will give exactly the same mean. So this is all we need. We just need to compute the Carl-Theodori theorem. And the original data for the mean is just P for the original data. For the matrices, we take the matrices and compute Carl-Theodori for the matrices. So it looks like this. We take the original points with the weights. So if you want the mean, it's just 1 over n, which is the same as the sum, up to a factor of n. And then we replace them by the d+1 points that we get from Carl-Theodori theorem. So most of the points will be 0. And we can choose a small subset that will give us the exact mean, which means that we can only track this small subset and preserve the mean. And for higher dimensional space, it will also preserve the rotation or the eigenvectors that are related to the SVD. The problem with this approach, OK, let's see how it works in the experiments. So we run many experiments, and the phenomena that we saw is that every few frames we compute a new coset. And as you can see, unlike a random sampling, which is the red line, So this is the how many frames you compute a new course set. And this is the error, the sum of square distances compared to the optimum. And if you just take random points, it doesn't matter how much frame you use because just a random set. Using course set, after if we approximate it every single frame, we get optimal solution. But even if we approximate it every 3 points, we still get a much smaller value than just random sampling. And again, when we take the camera farther from the drone, we actually get better and better results. Now, in machine learning, we have huge matrices. And the dimension, like in the PageRank problem, the dimension is the number of people. So you have n by n matrix, and you want to sum the weighted mean of this matrix. But now d equal n, which means that the dimension is huge, and you cannot just take d plus 1 points because it means you take all the metrics to the course set. So what we do instead, the first solution was d plus 1 point, and the sum of the original data, the sum of the original vector, was the same as the sum of the course set vector, only d plus 1 vectors, but we paid d plus 1. The next result is that we can pay only 1 over epsilon, which is independent of both the dimension and the number of points, only the error, and the sum is only approximated by the 1 over epsilon point of the course set. An approximated means that you have epsilon multiplied by the variance of the point, and in PageRank is simply epsilon. So that's how we compute it for a PageRank, but how we compute approximated Carr-Theodori theorem. So now we don't want to compute the exact mean of the point, but just some epsilon approximation for the mean. So for simplicity, suppose that you scale the data and translate it so the mean is the origin, and you have all the points scaled on the unit circle, on the unit ball. How we find a good approximation of the mean that is a convex combination of only few points on the unit sphere. So this is the trick. It's essentially related to convex optimization. You start with an arbitrary point. This is the first point in the course set. And then you choose the farthest point. So if you're lucky, the farthest point will be exactly on the other side, and the mean of these 2 points will give you the original mean. Usually you're not lucky, and the farthest point will be something like this. But you can still do your best. Using these 2 points, you can approximate the mean by these red points, which is only between these 2 original points. And you see the original center was different distance 1 to the mean. Now we get closer to the mean. Now in the next iteration, we find the farthest point from this red circle. Again, if we'll be lucky, it will be exactly here. And we have 3 points, a convex optimization of a convex combination of 3 points that will give us the mean. If not, we just take the farthest point and use this one and project the mean, the origin on these 2 points to get a better approximation. And the main result is that we continue to repeat this 1 over epsilon times. And the main claim is that no matter what are the points, after I iteration, this distance will be 1 over I. So 1/2, 1 over 3, 1 over 4, 1 over 5. So after 1 over epsilon iteration, you get epsilon distance to the mean, no matter what is the input. So you can see this proof in my website. This is the ICML paper. But this was essentially allowed us to compute the course set for the PageRank problem, and eventually high-dimensional problems where we want to compute the sum of vectors very fast with only some epsilon error, but on memory that independent of both the number of points and the dimension of the points. Before we go into question, I just suggest some open problems. There are many, many open problems. First, we want more course sets for deep learning. This one is just from today for topological data or topological problem, maybe triangulations. More course sets for sparse data. Autonomy, cars, robotics, maybe more application-related course sets. And now the issue is that we have communities of speech recognition, computer vision, and physics, but it would be nice. But actually, when you, for example, want to have an autonomous car, you need everything. If you have application on the mobile phone, you need both speech recognition and image in the same time, and you have GPS data. So we really want core sets, or in general, optimization algorithms for sensor fusion that take different kind of data and find optimal solution for all the data together. And we need both theory guides for this and practical guides to define the right problems. One of the popular things today is about privacy. We have a huge project for Samsung about how to do private core sets. So the idea is that we have on the Internet of Things, Alexa and everything at home, and the company says, first of all, we're not sure that we can take all the data from you because the government won't let you just take pictures and just record everything in your apartment. The second thing is we don't need all this information. We just want to know how much time you say Coca-Cola this month or something like this. So the question, can we collect statistics on people while preserving their privacies in some provable way called differential privacy? And surprisingly, in Stock 11, with Kobe Nissim that just won the Gedler Prize, we show a surprising connection between core sets to talk about compression and the differential privacy to talk about privacy. Essentially, we show that if you have core sets for a problem, it means that you can publish statistics that preserve privacy. This is a Stock 11 paper. So it's a theoretical paper, and we hope to publish more code that implement these core sets. A new project, we hope to publish it in the end of the month with Shafi Goldwasser, and also Dia Kavya now help us a lot. In the case of homomorphic encryption, in short, homomorphic encryption means, can you send the encrypted data to the cloud, and when our algorithms, like emails on the encrypted data, get the result back from the server, and then open it, decrypt it, and read the data. So the server will help us with the computations, but will not have a look on the data. This is called homomorphic encryption. The main issue for many years is that in theory, the problem solved. In practice, it takes half an hour to multiply two numbers between 1 and 10, if you download the code from the web, for the internet. And using core set techniques and Sketch, we show that we can do this much, much, much efficiently on hundreds of megabytes. And the idea is not to solve the problem on the cloud, but just compress the problem for you on the cloud, and you will solve the problem fast on your laptop. So I hope that we can publish it in the end of the month. Last thing, more software library, maybe related to CGAL or maybe other libraries for computing core sets, both for streaming data, real-time data like in robotics, and on the cloud. And that is, I think, this is my group in Haifa. And if you're around Haifa, you are welcome to visit us and maybe work on some problem with us. Thank you very much.